Okay, so now we are recording. Okay, so Bismillah ar-Rahman ar-Rahim. In today's class, inshallah, we study the serial communication. So in the serial communication, that means we have devices, and between these devices, we have here the communication. So the first type of communication that we have is the parallel communication. So we have two devices, device one, and we have the device two. So the first type of communication is to use parallel communication. So device one can be, for example, microcontroller. Device two can be any other device. It can be microcontroller. It can be sensor. It can be LCD. It can be memory, EEPROM. It can be any other device. So here we can use here the parallel communication for the data. Okay. So what is the disadvantage of using parallel communication? Let's suppose that we are designing a system in which we need two LCDs and we need to connect, for example, 5 sensors. In that case, can we do this in parallel communication? Is it possible? If every device needs, for example, 10 or 8 bits, is it possible to have all these numbers input output? No. Okay, so this is the first disadvantage of using parallel communication is we need many input output pins. So the second disadvantage is that if you have wires working like this in parallel, so if you have here, if you are passing information through the wire, this will generate a magnetic field here. And this magnetic field can perturbate or can change the values of the near wires here. So here we are talking about the mutual inductance, okay? So we can send here a byte, you receive another byte. That's why here in parallel communication, we cannot have long wires. So that's why here it's better to use serial communication. So if you use serial communication, we can use just here one wire or two wires. We can add the ground. So here it depends on the protocol that we are using. So if you are using the USART, which is the protocol that we will see today, we need one line for sending the data, one line for receiving the data, and we need just the ground between the two devices. So this is the USART protocol. Okay, universal, synchronous, asynchronous, receiving, and transmission. Okay, so here you can see that we are using just two wires to connect the two devices. Now, if you have many sensors, so we can use, for example, two wires for every sensor. So here we can hold or we can manage this. Okay. Now there are many standard or many protocol of serial communication. Can you give me some example of serial communication protocol? Yeah, like you started your project now, you know what are the serial communication protocol that are available in the market with the electronic component. Try to use your mic to answer, or if you want, you can use the chat. Yalla Shabab, what are the serial communication protocol that you know? Very good. So we can use the UART, we can use USB. So USB is for Universal Serial Bus. Okay, UART is the USART, but here you are using the asynchronous mode. So in asynchronous mode, it is called UART. Okay, Universal Asynchronous Mode, receiving and transmission. So your colleague here give us these values. Do you know other types of communication? So if you have a microcontroller and you want to connect a sensor to your microcontroller. Okay, so we have here the microcontroller and you have here any device. Let's use LCD for example. So if you want to connect this LCD in parallel mode, we need at least 8 bits. So at least we need 4 bits for the data. So generally we have 8 bits for the data, but you can use the reduced mode, 4 bits for the data, and you need 3 bits for the control. And here we need at least 7 bits to to connect just one LCD. If you need to connect another LCD, you need also 7 bits. Okay, that's why here we are using generally if you have many devices that are connected with serial communication. So in the market, we can find I2C LCD. So you have the LCD itself, and in the back of the LCD, there is another board here, which is the I2C. So this I2C board will take the data in parallel and send it and convert it to serial data. Okay, so here we have seen the some communication protocol like the UART, which is Universal Asynchronous Receiving Transmission. Okay, so here we are talking about the RS-232 protocol. Of the USB, which is Universal Serial Bus. We'll see also in the next chapter the SPI, and you'll see the I2C. Okay, so we'll see this. Today, inshallah, we study the UART. Then in the next class, inshallah, we'll study the SPI and the I2C. Okay. Now, let's start with some terminology. Now, if you have to connect two devices in serial communication, there are two modes. The first mode, it is called synchronous mode. The second mode is the asynchronous mode. So in the synchronous mode, you can see that the two devices, they are sharing the same clock. So this is called synchronous mode. And in asynchronous mode, you can see that every device has its own clock. So this device has its own clock. This device has its own clock. So this mode here, the second mode, is the asynchronous mode. The first mode is synchronous mode. Okay. Now, if there is no common clock, if you are using in asynchronous mode, you have to have a communication protocol. Yani the receiver, how does the receiver know that the transmitter is sending? Here we need communication protocol. So me, for example, I'm talking with you by using the English language. So here our communication protocol is the English language. So same thing here, if you are in asynchronous mode, you need a communication protocol. So the communication protocol that we are using generally is that here we have the idle mode, okay, and then we have the start beat. After sending the start beat, we have here the data itself, and then we have the stop. After the stop beat, here we return back to the idle mode. So here what are we doing? We are framing the data. So this is the data, 8 bit of data. We are framing the data with the start beat and the stop beat. Okay. If you have synchronous mode, no need to do this. We just here to use, since they are using the same clock, so the transmitter, so one of the devices will generate the clock, and here we just need some pulses for synchronization. So here we don't need the start and stop beats. Okay, but we can have the start condition, we can have the stop condition, but we are not framing the data between the start beat and the stop beat. We'll see all the techniques. Okay. Now, if you have just one transmitter sending the data to the receiver, we have here one way of data. Okay, the transmitter is sending to the receiver. This is called the simplex mode. Now, if both they are sending and both they are receiving, so here we have the first device is a transmitter and receiver. The second device is transmitter and receiver. Here we are talking about the duplex mode. And in duplex mode, we have two possibilities. If the two devices, they are sharing the same line of communication. We have one line of communication. In this line, we will send. So in this line, we can send and receive the data. Here we have just one communication line, one communication channel. So this is called half duplex mode. Half because they are sharing the same line. And if you have two different lines, one for sending and one for receiving, so this is called the full duplex mode. Now let's start with the 3-wire asynchronous serial interface. So here we are talking about the RS-232. So in the previous computer, or in the old computer, we have this connector like this one, which is similar to the VGA, but here we have 9 bits. Okay, we have a total of 9 pins. So this connector is called the DB9 connector. And this DB9 connector we are using here, the RS-232. Okay, so here we have So here we have the DB9 connector. Okay, so we have 9 bits. From this 9 bit, we have here 1 bit for receiving the data, which is the bit number 2. This is the RX for receiving the data. We have 1 bit for the transmission of the data, which is bit number 3. So this is our TX. And then here, the bit number 5 is the ground. Okay, so by using this connector here, we can connect two devices. So how can we connect two devices? Let's suppose that we have two microcontrollers, microcontroller 1 and microcontroller 2. So the first microcontroller has a TX pin. The TX pin of the microcontroller 1 should be connected to the RX pin of the microcontroller 2. And the TX pin of the microcontroller 2 is connected to the RX of the microcontroller. So if you have two microcontrollers from the shape from the same company, or if both they are using the CMOS and the same voltage, for example, 5 volt here, 5 volt here, you can directly make the connection. Okay. So if you have, for example, one microcontroller with one PC. So here we have an example. So here we have the microcontroller, we have the TX pin, and we have the RX pin. So the TX pin is the RC6. Shabab, the port C is the port that we are using for serial communication. So in port C, we can find the UART, you can find the SPI, and you can find also the I2C. Okay. Now in port C, the pin C6 here is the TX pin, and the pin C7 is the RX pin. Now this is the DB9 connector. You can see that here we have the ground. Okay. So the two devices, they should have the same ground. Okay, so this ground should be connected to this ground. Okay, and here generally for the computer we are using the TTL technology, and for the microcontroller we are using the CMOS technology. So here they are not using the same technology. That's why here we need something in between to adapt the voltages. So the voltages here in the DB9 connector can be up to 20 volts. And for the microcontroller, we are using a voltage of 5 volts. Okay, so we need something to adapt the voltages, and this something is the IC, is the MAT232 IC. So if you have to design something, if you have, for example, design project and you want to connect the project to the DB9 connector, in that case, you have to use the MAT232 IC in the two. So this is the adapter. We need just to add here two capacitors. Okay, and you can use here the pins 11, 12 and 13, 14. Okay, so you have the TX is connected to the pin number 11, which is the transmission input, and here we have the transmission output, which is 14, should be connected here to the RX. And here we have the RX should be connected to the pin number 12, which is the receiving output. And here we have the receiving input should be connected to the TX of the DB9 connector. Okay, so the RX, the TX is connected to the RX, and here the RX is connected to the TX. Okay, now in this chapter we'll see how to use this port as asynchronous mode. So in asynchronous mode, we have seen that we need to frame the data between the start bit and the stop bit. So let's suppose that this is our data. We have 8 bits of data. You can see that we are adding here the start bit and we are adding the stop bit. We are making here, we are framing the data between the start and the stop bit. Let's suppose that our data is the letter A. Okay, so to display the letter A on an LCD, for example, we have to send the ASCII code of the letter A, which is, for example, here, this value. Okay, so with the decimal, you can convert this 1, 2, 4, so it is here 4, 1, so it's 41. Okay, now how to send this letter A? You have to take this value, these 8 bit, and then we can add the start bit and the stop bit, and then we can send the data. So here we start from the start bit. So the start bit goes first. Then we have the LSB. So we send here the value 1, then 0, then 0, then 0, then 0, then 0, then 1, then 0, and finally you have the stop bit. Okay. So here we are framing the data between the start and the stop bit. Now, if two devices will be connected together, they should share the same configuration, okay, the same transmission parameter. So that's why here we have a standard for the transmission parameter. So here for the transmission parameter, they should have the same transmission rate. For example, 9,600 beat per second or 19,200 beat per second, etc. Okay, they have to use the same number of stop bits. So we can have 1 or 2 or 1.5. So generally we are using 1. And they have to send this, we have to share the same word length. So you have 8 bits of data. So the two devices, they should have the same number of bits for them. Okay, so you have an example of the idle mode. Okay, then we can have the stop bit. So we can have 1, 2, 1.5, etc. And then we have the data. Sorry, here we have the idle line, then we have the start bit, then we have the data, and finally we have the stop bit, and then we return back to the idle mode. Okay. Now, if we send the data serially, there is a risk that we don't receive the same data. We can send, for example, 0xAA. Okay, we can receive 0xAB. Now, how to check if the transmitted data is it correct or not? Here we have to use, we have to check, we have to control here the data, is it correct or not? Okay, now there are many techniques. So the first technique is to use the parity. So what is the parity? So the parity here can be even or odd, and we can use even parity or we can use odd parity. What does mean even parity? So let's suppose that we want to send 1 byte. Okay, so here you have this data 0, 1, for example, 0, 1, 0, 1, 0, 1. Okay, now in addition to this data, we'll send another bit, which is the parity bit. Let's suppose that we are using an even parity. What does mean in even parity? And if the number of ones is even, we will send 1. So here, what is the number of ones? 1, 2, 3, 4. We have 4 ones. 4 is even, so we'll send here 1. Now, we'll send the data itself, and then we'll send the parity bit. Okay? The receiver will receive the data, and we receive also the parity bit. And then the receiver has to calculate the parity bit from the received data, and then this bit should be compared with the received parity bit. So here the receiver has to calculate the parity and then compare it with the received parity. If the received parity is the same as the calculated parity, that means there is no problem. Now let's make a simulation. Let's suppose that here we receive 0, 1, 0, 1, 0, 1, and here 1, 1. So what is the number of bits here? 1, 2, 3, 4, 5. So 5, yani the parity bit should be 0. So 5 is not even. It is odd. So the parity bit should be 0. But here we receive the parity bit of 1. So 1 is not 0. That means there is 1 bit of error. So the disadvantage of this technique is that if you have 2 errors, this technique cannot detect. And here this technique can detect the number of errors that are odd. Okay. Now let's see the convention of the transmission. So here we have to give the speed or the baud rate. The unit here is bit per second, and then we have to give the x, which is the number of bit in the words, and then we have to give a, which is the parity. So for the parity, we can have n, we can have e, or we can have o. n yani known, e yani even parity, and o yani odd parity. And z is the number of stop bits. Yeah, and if you read from the data sheet, you have, for example, like this, 38,400 bit per second, 8 E1. What does it mean? That means that the communication should be at this baud rate. So this is the speed. Or we can call this the baud rate. Or we can use just BR. Okay. So this is the baud rate. Okay. And then this A, that means the data is 8-bit data. We have a data of 8 bit. This E is the parity. So here we are using even parity. And this one here is the number of stop bits. Is this clear? So this is for the parameter of the communication. Okay, here we have another example. So here, what is the difference? Here we have the speed. This is the baud rate in bit per second. And here n, which is the length of the data. And here yani, we are not using parity. So known for the parity, and we are not using parity. And one here is the number of stop bit. Now, what are the types of the error that we can have? We can have a framing error. That means we have the data, and we are adding here the start beat and the stop beat. So let's suppose that the receiver is waiting for a stop beat, and the stop beat is 1, but the receiver received here a stop beat of 0. And here there is a problem of framing the data. This is called framing error. And generally we have one flag to detect this error. Okay. Another type of error, which is the overrun error. So overrun error, that means occur when a new byte overrides the earlier byte before the receiver complete reading the earlier bytes. That means if we send the data serially, so this is the first device, this is the second device, and here we have serial communication via any pin, so you have the pin RX. Once a byte of data is received, so this byte of data will be saved in one register. So it is RC reg, RC register. So if you receive anything serially, it will be saved into the RC register. Receiving the data will not be in one cycle, because to receive 1 byte, we need here at least 1 cycle for the start beat, 8 cycles for the data, and 1 cycle for the stop beat. So we need at least 10 cycles. That's why here it takes time. So once the device number 2 or the receiver received a byte of data, the data is now in the RC register. So now here we have to read this data. Okay, so how to read the data? We can use here the move F or move FF. We have to read the data from the RC register. Now, if a microcontroller received 1 byte of data, and the data here is in the RC register, and the user comes. Okay, so the first byte is not read, and there is another byte that is that came here. So here we have what we call an overrun error. So we have 1 byte will override the earlier byte. This is an example of overrun error. Now, to check the error, we have seen that you can use the parity. You can also use the checksum. The checksum here is very important. So how the checksum work? Let's suppose that we want to send 5 bytes of data. 1, 2, 3, 4, or 4 bytes. Okay. So the transmitter will send these bytes. Okay. And we send also the XOR of all these bytes. Okay, so here we have any value 0xAB, here we have CA, here we have 0, 3, A, 1, and then we will send the XOR of all these values, and AB, XOR CA, XOR 0, 3, XOR A1. Okay, and this byte also will be sent. Now the receiver will receive the 4 bytes, and we receive the XOR of these 4 bytes. Now the receiver has the data, so the receiver can calculate the XOR of this data. And then the receiver has to compare the received XOR with the calculated XOR. If the received XOR is the same as the calculated XOR, yani it is okay, so there is no problem of, we don't have error in the communication. But if the calculated XOR is not the same as the received error, but the received XOR, that means there is a problem. So this is what this means, check sum error check. Now we'll study the serial port. Now we'll start the configuration of the serial port. So here we are using the USART, which is the universal synchronous asynchronous receiver transmitter. So it can work in both in synchronous mode and in asynchronous mode. So this S is for synchronous and this A is for asynchronous mode. So the synchronous mode can be used to transfer data between peak and external peripheral, like ADC, EEPROM, etc. The asynchronous mode is used to connect the peak 18 to a PC, for example, by using the serial bus, etc. So generally, if the devices they are close to each other, for example, here we have one PCB, and here we have the microcontroller, we have here an LCD, we have an EEPROM, and you want to connect these devices together. So if they are in the same area, they are close each other, in that case you can use the synchronous mode. And if you have two distinct devices, so here you are designing your system and you want to connect your system to PC by using the serial port. So the PC has its own clock, your system has its own clock, and then here you can use the asynchronous mode. Okay, so if you have devices that are in the same area, generally you are using the synchronous mode. If you have distinct devices, generally you are using the asynchronous mode. Okay. Now, let's understand how does it work. So the USART is already embedded in our microcontroller. What does mean embedded? And we will not send the data bit after bit by ourselves. We will not write a program to send the first bit, then send the second bit, or send the third bit, etc. But here we have the first device, and you have the second device. If you want to send any byte of data, so here we have the TX pin, here you have the RX pin. Okay, so let's suppose that here we want to send the value 0xAB. Okay, so here there is a register named the TX register. You have just to put this value to the TX register. And first of all, you have to make the configuration of the speed. Okay, so generally here we are talking about the speed. After making the configuration, if you want to send any byte, just put your data to the TX register, and the CPU will start directly sending the data. The CPU will take the data, which is 0xAB, using 8-bit. It will frame the data with the start bit and stop bit, and we will start sending the data bit after bit. And we as a programmer, we don't care about this. We have just to make the configuration and just put the data to the TX register. And the CPU will start sending the data via the TX pin bit after bit. Once the data is sent, the microcontroller will generate an interrupt, which is the TX. We have here a flag, which is the TX interrupt flag. The TX interrupt flag will be equals to 1, yani the data is already set. Yani while the CPU is sending the data, you can do any other task. You can execute any instruction, any part of the code. Okay, so if you want to make serial communication, you want to send this data, just put your data to the TX register, and then we can go make any other task. Once the data is transferred, so this will generate an interrupt, so the TXIF will be equals to 1. So this is what this means. We have an embedded. So this is what this means. The UART is embedded already in the microcontroller. Okay, so it is implemented already. We are not just doing this by program. Okay. Now, same thing for receiving. So the device number 2, if it is a microcontroller, so device number 2 will receive the data serially. The data will be deframed to remove here the start bit and the stop bit, and the data will be here in the RC register. And then the user has to just read the data from the RC register. So when there is a data available on the RC register, this device will generate an interrupt. So here we have the RCIF will be equals to 1. Yani if the receiver receives a byte of data, after finishing the receiving of the data, the RCIF will be equals to 1. So the RCIF equals 1, that means we have to read the RC register. And for the transmitter, if you want to transmit the data, you have to put the data to the RC register, and the CPU will start sending the data bit after bit via the TX pin. Once the transmitter finishes, the sending the data, this flag will be 1. The TXIF will be equals to 1, and this will generate. Any question about this? No question. So in today's class, we'll see how to make the configuration. Once we have done with the configuration, the program will be very simple. If you are sending the data, just put your data to the TX register, and the CPU will start sending the data serially. If you need to send another byte of data, you have to wait for the flag to be 1. If the flag is 1, yani the CPU already sent the previous byte, you can send the next byte. And if you are reading data, so if you are in receiving mode, you have just to wait for the flag to be 1. If the flag is 0, yani the CPU didn't receive anything. Okay? Once the CPU received a complete byte of data, the flag will be 1, the RCIF is 1. So here you have to check the RCIF. Once the RCIF is 1, then we receive a data, and then we can read it. So how to read it? We can read it from the RC register by using move F or move FF. So as an example, let's suppose that you want to send the byte AB, 0xAB. So how to do it? You can use move LW, 0xAB, and then move WF, TX register. So the CPU, while the CPU executes this instruction, it will start sending the data serially via the TXP. Now, for the device number 2, microcontroller 2, so the microcontroller 2 has to check the RCIF by using bit5 skip reset or by using bit5 skip reset till the flag becomes 1. If the flag becomes 1, yani there is a byte of data that is already received, then we can read it. So here you can use the polling technique, or you can use the interrupt technique. So both are available. Okay. Now, first of all, you have to understand how to make the configuration. Once we have done the configuration, the rest is very easy. So if you want to send, I repeat, just send the data to the TX register. And if you want to read, you can read the data from the RC register. Okay, so similarly, the device number 1 has also the RC register, and this device also has a TX register. So if this device will send to this device, same thing, the data will be sent by the TX pin, and here the receiving will be by the RX pin. Okay, now let's start the configuration. For the configuration, we have many registers, but for every register we need just some bits. For example, from the baud core register we need just 1 bit, which is the BRG16. Okay, now these two registers, serial port baud rate generator and serial port baud rate generator high. So these two registers, they give us a value n that is proportional of the baud rate. So here, let's suppose that the baud rate is 9,600 bits per second. So instead of writing this value directly, we'll use a formula that gives us the value of n. So here, n equals f of the baud rate, which is 900, 600. So this formula, you can find this formula from the datasheet, and we will discuss this formula. So why do I have here a formula? Because here the value of n depends on the speed. Is it high speed or is it low speed? It depends also on the type of communication. Is it synchronous or asynchronous? And also it depends on the mode that you are using. So we can use the 16-bit mode, or you can use the 8-bit mode. So we'll see a table that summarizes everything. Okay. Now, for the moment, these two registers, they will give us the value of the baud rate. Now, if you are in 8-bit mode, like the timer, you are using just this register, which is the serial port baud rate generator. If you are in 16-bit mode, you have to use both. You have to use the serial port baud rate generator and the serial port baud rate generator high. So these two registers will be used to write the value of n. So this value of n is nothing but the value of these two registers. And this value of n is proportional to the baud rate. And the relation, we will see this relation in the next slides. Okay? Now, Here we need the baud count to select between 8-bit mode and 16-bit mode. These two registers are used for the baud rate. Okay, and then for the status, here we have two status registers, one for the transmission and one for the receive. Okay, and for the interrupt, here we have the flags. Okay, now these two registers, they are used to send and to receive. So after making the configuration of these registers, so we have here 5 registers that we can use for the configuration. 2 of them will be for the value of the baud rate and the other are for the configuration. Okay, now once we have done with the configuration, we can send the data via the TX register and receive the data from the RC register. So let's start with the baud count register. So from the baud count register, we need just one bit, which is the BRG60. So if this bit is 0, yani you have here. So if you don't have 16-bit mode, yani you have 8-bit mode. If this bit is 1, yani you have 16-bit mode. Okay. Now let's see the TX status register. So the TX status here has two main bits or 3 main bits. So the first one is the TX enable. So if you want to send something, this bit should be 1, TX enable. And here you have the synchronous bits. So if you have 0, yani asynchronous mode. If you have 1, yani synchronous mode. And here you have the speed. So here you have BRG, baud rate generator, H for high speed. So this bit if 0, yani low speed. If this bit is 1, yani high speed. Okay, so these are the main bits that we need from these registers. Now let's have how to find the value of n, which is the value of the two registers, serial port baud rate generator and serial port baud rate generator high. Now let's suppose that we are using asynchronous mode and you are using, for example, high speed or BRG H equals 1, and here we are using 16-bit mode. So let's suppose that you have these 3 values: 16-bit mode, asynchronous communication with BRGH equals to 1. Okay, so what is the formula that you have? So we have to check here. Asynchronous mode, yani you have 0, and BRG16 equals to 1, we have 16-bit mode, and we have BRGH equals to 1, so we are here in this situation. Okay, we have asynchronous mode, so the synchronization bit is 0. We have BRG16 bit, so BRG16 is 1, and we have high speed, so here the BRGH is 1. So if you are in this situation, you have to use this formula. So what is this formula? So this is the baud rate. So here we have the baud rate equals to what? Equals to the frequency of the oscillator divided by 4 multiplied by n plus 1. So what is the value of n? N is the value of the two register, the serial port baud rate generator, if you are in 8-bit, or both if you are in 16-bit. Is this clear? So this n will give us the value of the two registers. If you have, for example, asynchronous mode, let's take another example. We have asynchronous mode and 8-bit and BRG H equals to 0. So here BRG we have 8-bit mode, so BRG16 is 0. We have asynchronous mode and BRGH is 0. That means we are in this situation. So in that case, we have to use this formula. So it is this formula. So this is the baud rate formula. So the baud rate equals to the frequency of the oscillator divided by 64n plus 1. So generally we have the baud rate, we have the frequency of the oscillator, and we have to find the value of n. So let's suppose that we are using this formula and we need the value of n. So what is the value of n here? So we can multiply here. So the frequency of oscillation will be 64 or 64, let's see, 64 multiplied by n plus 1 multiplied by the baud rate equals to the frequency of oscillator. Okay, so here what is n plus 1? So n plus 1 equals to the frequency of oscillator divided by here we have 64. Okay, so here, 64 multiplied by the body weight. So this is n plus 1. So we need n, and here we have to make it minus 1. So now our n is the frequency of the oscillator divided by 64 body rate minus 1. Write it here. So the value of n equals to the frequency of the oscillator divided by 64 multiplied by the body rate. Okay, so let's suppose that here we have a speed of 9600 beat per second. So it should be small b or beat, not white. Okay, so this is the baud rate. Okay, and let's suppose that our crystal frequency equals to 4 megahertz. In that case, we can calculate the value of n. So the value of n here will be the frequency of the oscillator, and 4 multiplied by 10 to the power of 6 divided by 64 multiplied by the baud rate, which is 9600. Okay, so let's calculate this by using the calculator. So here what do we have? We have 4 followed by 6 zeros, okay, divided by 64 divided by 9600. So here we have a value of 6.51. So here our value of n. So in this example, n is 6.51. Okay, so 6.51, you have to make minus 1. Okay, so it is, just a moment, so here we have 6.51 minus 1. So here we have to make the minus 1. Okay, so this value minus 1. Okay, this is our n, so we have to make minus 1. So 6.51 minus 1, so here the value will be 5.51. Now, what is the nearest value to 5.51? So the nearest value is 6. So here, in that case, we can select n equals to 6. Okay, the nearest value to 5.51 is 6. So we can use n equals to 6. So what is this n? So here we are in 8-bit mode. So this n is the value of the serial port baud rate generator. So the serial port baud rate generator here has the value 8. So this is the value of the serial port baud rate generator, which is the decimal value 8. Okay. Now, if you have 16-bit mode, in 16-bit mode, generally we have n that is greater than 255. So let's suppose that we have n equals to 1023, for example. So I will here everything, and I will share my screen so that you can see the calculator. Okay. So now I'm sharing my screen. Okay, so let's have any value of n. Let's suppose that we calculate the value of n, and the value of n here, let's use 2029. Okay, this is the value of n that we found. So from this value, we have to convert this value to hexadecimal format. Okay, so let's use the calculator. Here we have to go to the programmer mode. So the value in decimal is 2029. So you can see that it is 7ED. So here the value is 7ED. So this value is nothing but 0x 7ED. So this ED is the value of serial port baud rate generator, and the 07 is the value of the serial port baud rate generator. So you have to make the configuration of the baud register. And you have to select 16-bit mode or 8-bit mode, and you have to make the configuration of the TX status register. And finally, you have to give the value, you have to find the value of n, and then from this n, you have to give the value of these two registers. In the exams, you have this table. Okay. So let's see an example. For a device with a frequency of oscillator 16 megahertz and the baud rate of 9600 in asynchronous mode, 8-bit mode with BRG, so 8-bit mode BRG. Okay, so here we selected BRG H equals to 0. Let's add here BRG H equals to 0. Now, what is the formula that you have to use here? So we have 8-bit mode, asynchronous, and BRG H equals to 0. So here we are in this situation. So BRG H equals to 0, BRG 16 is 0, we have synchronous mode, so we have to use this formula. So what is the value of n in that case? Okay, so the n here, you have to extract the value of n, which is the frequency of the oscillator, divided by baud rate, divided by 64 minus 1. Now the frequency of oscillator is 16 megahertz. The baud rate here is 9600 beat per second, and you calculate this to find 25.042. So the nearest value is 25. So this is the value of n. So this n is the value of what? Of the serial port baud rate generator, because here we have just the 8-bit mode. So you can see that here our n is less than 255. Okay. So here, how to load this value into the serial port baud rate generator? We can use move LW, the decimal value 25, and then move WF, the serial port baud rate generator. Okay, so now we selected n equals 25. Let's calculate now the baud rate with this n, because we didn't select 25.042. We selected 25. So if you select the 25, you can calculate again the baud rate by using the same formula. You find here 9615 beat per second. So here we have just an error of 0.1%. So this is okay. Okay. Now, if we summarize, these are all the registers that we need. Okay, from the baud-con, we need just the BRG 16-bit to select between 8-bit mode or 16-bit mode. From the TX status here, if you are sending, you have to make this bit equals 1. Here, generally we have 0 because generally we have the asynchronous mode. And here you have to select the high speed or the low speed. If you selected low speed, you have to use the formula according to the low speed. If you selected high speed, you have to use the formula according to the high speed. Now we have another register, which is the RC status. So the RC status has this pin, which is very important. So this is the enable of the whole serial communication. So you have serial port enable. If you want to read or if you want to send data, this bit should be equals to 1. This bit should be always 1 if you want to send or to read. Okay. And you have just here another bit, which is continuous reading enable. If you are reading data continuously, you are receiving 1 byte after byte, byte after byte, byte after byte. In that case, the continuous reading enable should be 1. The rest here, there are errors or flags or configuration 8-bit, 9-bit. So generally you have 8-bit, so no need to use the TX9 or RX9. So the rest you can use 0 for them. Okay, so if we summarize, 3-bit for the configuration and these 2-bit for the baud rate, and then you can send and receive the data normally. Now, for a byte of data to be transferred via the TX pin, you have just to place the data to the TX register. So the TX reg is a special function register, okay, and we can access to this register like any other register. For example, move LW 0x41, move WF TX reg. So this will start sending 0x41 serially via the TX pin. So 0x41 is the ASCII port of the letter B. Okay. Now, if you want to, for example, read from port B and send serially, you can use move FF port B, TXREG. This will initiate sending serially the value of port B. So port B is read as 8-bit, and then the CPU will start sending the data bit after bit. After framing the data, after adding the start and the stop bit. Okay, so if you want to send something, just put your data from the data bus to the TX register. The CPU will frame the data by adding the start bit and the stop bit, and then here the data will be sent via the TX bit. So here we have another register here. This is the TSR register, which is the transmit shift register. But we as a user, we can use only the TX register. Just put the data to the TX register, and the CPU will do the rest. It will frame the data and start sending the data bit after bit, starting from the X. So the CPU will not send 8 bit of data, but will send 10 bit of data. The data itself, plus the framing bits, the start bit and the stop bits. Now, same thing for the receiving of the data. So we are receiving the data from the RX pin, and then we are receiving the data and the start and the stop bit. So here the data, after receiving the 10 bit, the 10 bit will be saved in this register, which is the receiving shift register. Then the CPU has to deframe the data. Deframe yani remove the start and the stop bit. And then the data will be copied to the RC register. And we as user, we can read the data directly from this RC register. So how to read the data from the RC register? So we can wait for the flag for the RCIF to be 1. So if the flag is 1, that means there is a data available in the RC register, we can read it. So how we can read it? We can use move F if you want to if you want to send the data to the work register. So move F RC reg, 0. So this will move the value of the RC register to the work register. Okay, so we can, for example, use this technique if you want to send the value on port B. You are reading the value serially, and we are sending the data to port B. So we use move FF RC register, port B. So this will copy the value of the RC register to port B. We are receiving data serially, and we are sending the data in parallel to port B. So these are the different registers. So for the TX status, so as I explained, we need the TX enable bit. So if you want to send data, this bit should be 1. Generally, for the synchronization bit, you have generally the asynchronous mode, so the value is 0. If you have synchronous mode, you can make it as 1. Okay, and then here you have the BRG8, BRGH. So here you have high speed or low speed. Okay, so here it depends on the value. It can be 0 or it can be 1. The rest you can assume that they are zeros. Okay, so here the clock source select, we are not using this because we are in asynchronous mode. Here the TX9, we are not using this because generally we have 8 bits of data. The TX enable here is very important. If you are sending the data, this bit should be 1. If you are just receiving, you can make it as 0. The synchronous bit here is 0 because generally we are using asynchronous mode. Send break character, generally we don't send break character. And here we have the transmit shift register status. So here it is read only bit. So this will give us an information about the TS. Okay, and the TX9D, so we are not using translation of 9 bits, so this bit is 0. And for you, you have to focus just on these bits. The TX enable 1 if you are sending, this bit is 0, and here you have to check the value of the high bit. Is it high or low? Okay, so generally in the question they are giving the value of the BRGH, or they are saying, for example, in high speed or in low speed. This is for the TX status. Now for the RC status, we need principally this bit. So this bit will enable the serial port. So here the speed will be 1. So if this bit is 1, the serial port is enabled. Serial port means TX and RX. If this bit is 0, that means the serial port is disabled. You cannot send, you cannot receive. If you are receiving continuously, So the speed should be 1. If you are just reading 1 byte, the speed you can make it as 0. The rest you can make them directly as zeros. So you have framing error, overrun error, 9-bit, etc. So all these bits you can make them as 0. So here in the program, just focus on this bit, serial port enable, and if you are reading from this bit should be also 1. The rest you can make them directly as zeros. Okay. Now, if you want to use interrupt, you have one flag for the RC, one flag for the TX. So RCIF or TXIF. Now, if you are sending data, you have to put the data to the TX register. Okay, for example, here you have 0xAC. Okay. Now, while the CPU is sending the data, the flag is 0. Once the CPU finishes the sending of the data, the flag will be 1. Okay, so in programming, practically you have to wait for the flag to be 1. If the flag is 1, you have to send the next byte. Now, for the receiving, if the TX register is empty, okay, so this is the RC. Now, for the receiving, okay, so if this bit is 0, and the RC register is empty. But what does mean? And we didn't receive anything. This is the RC register. Now, if the flag RC reg or RCIF, if it is 0, yani the RC reg is empty. What does mean empty? Yani we didn't receive anything. We didn't receive completely any byte. Okay. Once a byte of data is received, so it is available here, and then the flag will be 1. So practically in the program, we have to wait for the flag to be 1, which is the RCIF. If the flag is 1, yani you have a data available into the RC register, you have just to read it. Once the data is read, the flag is cleared automatically. Okay, so you have to read the data in order to clear the flag. Now let's make now a program. Let's have here a read example. Now we have to write a program for PIC 18 to transfer the letter G serially, continuously. And you have to send the letter G, then send again letter G, then send again the letter G, and continuously. Okay. So how to send the letter G? You have to send the ASCII code of the letter G. Now, what are the configurations that we have to put here? We have the baud rate, 9600 bits per second. We have the crystal frequency. We have 8-bit mode with low speed. Low speed ايش يعني BRG H equals to 0. 8-bit mode and BRG 16 equals to 0. And from this baud rate, so طبعا we are using asynchronous mode. Okay, so here the synchronization bit equals to 0. So from the table we have seen if you have this configuration, so the frequency of the oscillator or the baud rate equals to the frequency of the oscillator divided by 64 n plus 1. We extract n, so here n will be the frequency of oscillator divided by 64 multiplied by the baud rate minus 1. So in this example, we calculate n is 15.27, the nearest value is 15. So this value here will give us the value of the register, serial port, baud rate G. Now for the configuration, we have to give the value of the TX status. We have to give the value of the RC status. We have to give the value of the baud-con register. From the baud-con register, we have the BRG16. And the BRG16 is 0, and the baud-con register is 0. And we have done with the baud-con register. No need to make the configuration. Now for the TX status, we have to enable the transmission. So the TX enable should be 1. We are using asynchronous mode, so this bit is 0. We are using low speed, so this bit is 0. So the rest you can make them as zeros. And here the value of the TX status. What is the value of the TX status? It is in hexadecimal, so here we have 0x, we have 2, and here we have 0. So if you make the configuration of TX status equals to 2, 0, that means we are enabling the transmission by using asynchronous mode in low speed. ايش باقي؟ باقي ال RC status. From the RC status, we have just to enable 1 bit. which is the serial port enabled. From the RC status, let's return back to the RC status. We have just to enable this bit. This bit should be 1. We are not reading anything, so here the bit should be 0. And what is the value of the RC status? 0x8, 0. So we can use move LW 0x80, move WF, the RC status, or we can just enable this bit. So we can, or we can just use bit set file. So here we have the RC status, comma, this bit which is the bit number 7. Or you can just use serial port enable. Okay, so we have done for the configuration. So for the configuration, first of all, we found the value of M. Then we have to give the value of the TX status. We have to give the value of the RC status, and we know the value of the protocol, which is 0. Once we have done the configuration, the rest will be very easy. So we have to move the value of TX status to the TX status register. We have the value of N is 15. We have to load this value to the serial port for the generator. So move LW, the decimal value 15, move WF serial port generator. So we are sending, so the TX pin should be output. So bit clear file to receive the TX pin. And for the TX status, we have to enable this serial port enable. So we can use the bit set file, the RC status, the serial port enable. So now, what is the program? We want to send the letter G serially. How to send the letter G? We have to load the ASCII port of the letter G. So move LW, the ASCII port of G, and then we can use directly move WF TX. Okay, but here we are waiting for the flag. Okay, so we can use this program, it's better. So move LW. So we can use move LW followed by move WF TX, and then we can wait for the flag. So we can have, so it is more logical. Okay, so move WF, or let's start with move LW, the ASCII code of the letter A. You can do it like this for A, the letter G, sorry. Okay, and then move WF, the TX array. So this will start sending the letter G serially. Now the question is to send this letter continuously. Now, I want to send this letter G again. But if we send the letter G again, if we use here L and then go to L, so this will erase the previous letter G. And while we are sending the first letter G, another letter G comes. So here we have what we call an overrun error. And we cannot send, or we can send the next letter G only after finishing the first transmission. So how can we check if we finished the transmission or not? We have to check the flag. So here we can use bit test file, skip if set, for example. So here, which flag we have to select, or we have to check? We have to check the TXIF from the PIR1 register. PIR1, comma, the TXIF. Now, if this flag is 0, we have to do something. If this flag is 0, we have to do something. Not just to wait. Yes or no? So here we can use go to check. You can use, for example, check, and then as long as this flag is 0, you can use go to check. Okay. And if this flag becomes 1, and the previous data is already sent, there is a skip. So now we can send the data. So we can use move LW again. So we can use the label in here, and we can use go to LW. So this is more logical. Okay. So we load the value, the ASCII code of the letter G, then we move it to the TX register, and then we have to wait for the flag. As long as the flag is 0, there is no skip. We have to go to we keep looking here. So here we are using the pulling technique. It's better to use the interrupt technique. but here we are using the pooling technique. Once the flag becomes 1, is skip. We have to send the next byte. So go to L. So here L will send the next byte, or will send again the asymptote of the letter G to the TX register. So this is an example of program, and here we have a microcontroller, and the microcontroller is sending the letter G via the TX pin. Okay, but here we don't have any information about the receiver. So the receiver, it can be any device, it can be another microcontroller, it can be a sensor, it can be any, it can be a computer, it can be any device. Okay. Now, if you want to do the same thing by using interrupt, what do you have to change? So you want to use the ISR of the TX. Okay. So here, if you want to use the same example with interrupt, so what do you have to keep and what do you have to change? So here we have to use the have to check the flag of the interrupt at the address 8. Okay, so here the configuration is the same. This is the value of the TX status. This is the value of the serial port module generator. The TX pin is output. We have to enable the serial ports. Okay, and then here we have to move the letter G and send the value to the TX register, and then we can use here the loop. Okay, now here you are sending the data. So to send the data, we are using interrupt. So we have to enable the interrupt of the sending the data, which is the TX interrupt enable. And the flag that you have to check is the TX interrupt flag. So this is for sending the data. Okay, so these bits, there are 2 bits of the PIE1 register, or the TXIE is from the PIE1 and the TXIF is from the PIR. Now, if you are receiving the data, so the enable is the RCIE, RC receiving interrupt enable, and the flag is RC interrupt flag. Okay, so the RC interrupt enable is also in the PIE1 register, and the flag is in the PIR1 register. And for the priority, we have the RCIP and the TXIP in the IPR1 register. So for the priority, we have seen that if you have 1 yani high priority and 0 means low priority. So the program will be like this. So we have the first part number 1, which is or 0 go to me. Okay, in the part number 2, we have to check if there is an interrupt coming from the serial communication or not. Yani if the previous byte already sent or not. So here we are checking the TXIF. If the TXIF is 0, what does it mean? That means here the previous byte is not sent. So it's not, or the CPU didn't finish the sending of the bit or of the byte or of the data. In that case, we have to return back to the main. But if this bit is 1, if the flag is 1, that means the previous byte is already sent. So here we have to use go to TXISR, and into the TXISR we have to send the next byte. Now, this is the TXISR. What do you have to do? If the flag is 1, we have to send the data to the TX register. So move WF TX register and then read 5. So you can see here that here we are not clearing the flag. So we didn't make here bit clear 5 PIR1 TXIF. Why? Because when you initiate the sending, the flag will be automatically cleared. Okay, so when you initiate the transmission, when you start sending something, the flag is cleared. If the data is already sent, the flag will be 1. Now for the main, we have here the serial port configuration, and you have the enable here. For the enable, we have seen that the TX is a peripheral source of interrupt, so we have to use the TX enable. We have to use the PE peripheral enable, PEIE peripheral interrupt enable, and we have to enable the global GIE. Okay, so bit set 5 the TXIE, bit set file, the PEIE of the int-con register, and bit set file, the global from the int-con register. In this example, you don't have a main task, so here you have just to make an empty loop over branch. That's it. So this is the same example by using the pooling technique and by using the interrupts. So in the interrupt, you have 4 parts. Okay. So the part number 1 is or 0 go to main. And part number 2 is checking the source of interrupt. So if the interrupt is coming from the TX, you have to use TX ISR, go to TX ISR. Okay, if not, you have to return back to the loop. So this is the part number 4, which is the TX ISR. Yani if the flag is 1, what do you have to do? If the flag is 1 and the previous byte is already sent, you have to send the next byte. So you have to use just move WF okay, to initiate again the transmission, and then you have the and part number 3 is the main. In the main, we have the configuration. So what do you have in the configuration? We have the input-output configuration. And here we have as output, we have TX as output. This is here the input-output configuration. We have to make the configuration of the serial port configuration by giving the value of the TX status, by giving the value of the serial port baud generator, and by giving the value of the serial of the RC status. Okay, and here we have the interrupt configuration or the interrupt enable. We have to enable the TX, we have to enable the peripheral, and also the. Any question about this? No questions. Okay. Now the program that we have seen is the program of the transmitter. Okay, we are transmitting data of one microcontroller, sending data serially to another device. Let's suppose that now the other device is also a microcontroller. So the second microcontroller is receiving the data via the RX pin. Okay. Once a byte of data is received, it will be copied here to the RC register. Now, since the second device is a microcontroller, now we have to prepare also the program of the receiver, the program of the second microcontroller. So this is what we'll do in this example. So here we have to write a program for PIC 18. So the second device here is PIC 18 to receive a byte of data serially and put them to port P. So here the main task is read the value that you have received serially from the RC register and send it to port P. And the main task here is to read from the RC rate and send to port P. Now we have the baud rate properties. And how to use the same baud rate, the same length of the data, the same number of stop bits, the same frequency. Okay, so here we have 8 bits. So the BRG 16 equals to 0. We have low speed. Okay, we have to use the same configuration and we have the same baud rate. And you have to use the same formula. With the same formula, you will find the same value of N. N now is 50. Now we have to make the configuration. For the baud-con, it is 0 because we have the BRG16 is 0. So the whole register baud-con, you can make it as 0. Now we have to give the value of the RC status and the TX status. For the RC status, we have to enable the serial port. And since we are reading continuously, so the continuously reading enabled here should be 1. So this bit CRAN, which is continuously reading enabled. This bit should be 1. The rest you can make them as zeros. Now for the TX status, do we need something? So we are not sending anything. So here the TX enable is 0, and we have low speed. So the speed is 0. We can just ignore the TX status. Now for the configuration, baud-con is 0, TX status is 0, and for the RC status, we have to load this value, which is 0x. We will have 1 plus 8 and 9, and here 0. So 0x 9 0 is the value of the RC status. Once we have done with the configuration, you have just to wait for the flag to be 1. If the flag is 1, we can read the data from the RC status and send it to port. So this is the configuration. We are giving the value of the RC status. We are giving the value of the serial port baud rate generator. We are reading from RX, so this bit should be input. and we are sending to port B, so port B should be out. Now we have to wait for the flag. Beat this file set. I have to check this flag continuously. As long as this flag is 0, we'll keep looking here. Once this flag becomes 1, we have to read the data and send it to port B. So move FF from the RC register to port B and then return back to R1. So this is how to make the program of this. Any question about this? So we have done for today's class. If we summarize, we have seen how to make the configuration of the serial port. We have seen an example of transmitting by using here the pooling technique and by using the interrupt technique. And we have seen an example of receiving by using the pooling technique. So at home you can check, for example, to make an example of receiving. You can make this example by using interrupt. So you can practice and do this. So if you are using the C, so here you have the libraries of the USART if you are using the micros. And you have done for today's class. Any question about this, Shabab?
No, all clear, thank you.
Okay, so thank you for attending. See you inshallah in the next